I'm going to say, okay, it's an open top, rectangular wooden box. Get myself a little diagram to work with. Now it's open top. And it's going to have a square base. And it has a capacity of 5 meters cubed. So that's going to be a volume measurement. And the cost, the material for the bottom costs $2 per meter squared, and for the sides it costs $1.60 per meter squared. And what we want to do is we want to minimize the cost of the box. So this is not memorized, I'm actually thinking about this. What I need is a function to minimize. And if I want to minimize cost, I need a function for what the cost is going to give us. Well, the cost is going to depend on how much material of each type I use. Now, the minimum amount of surface area is not good enough here because the bottom and the sides are made out of different materials and they cost a different amount. So I actually need a cost equation. So the cost equation is actually going to be $2 times the area of the bottom. And $1.6 times the area of a side. And how many of those are there? There's 4 of them. So the area of the bottom is x times x. 1.6 times 4. Area of a side is x times, now I don't have another value there. It didn't say that it's a cube, so I'm going to make it h. And it's going to be x times h. And that is my cost equation in terms of 2 variables. Well, 2 variables, not so good. I need to relate x and h. So I go looking for that, and I notice I haven't used my capacity yet. So volume is equal to 5 meters cubed. The volume for this regular shaped solid is area of the base times the height. So it's going to be area of the base times the height. I write that out so I don't forget. So it's going to be x squared times h equals 5. So h is going to equal 5 over x squared. And we'll consider that equation 2. And that's a different logic statement, so we'll make a different bubble. Thinking ahead, I'm thinking about my interval. And my interval's on x, because I'm going to end up getting a cost equation in terms of x only. It's going to be 2x squared plus 6.4x, and instead of h, we're going to put in 5 over x squared. That's subbing in 2 into 1. So the interval is on this variable that I'm interested in. I think we've talked about the fact that x can't be less than 0 and x cannot equal 0. Take a look at h. H must also be greater than 0. So what's the highest value x can be without interfering with h being greater than 0? Well, x can go on and on and on and on forever. This will get closer and closer and closer to 0, but mathematically, it'll never equal 0. And that's where mathematicians really annoy people. Because we say, yeah, it's an open bound. It's bounded on one side, but open on the other. There is no limitation on the size of x. And people get all upset. And they say, well, yes, there is. And yeah, if you're making a can, there are some limitations. But mathematically, this really interesting concept of a limit is kind of cool. So there we go. So there's my interval. Again, it's a bounded interval. It looks like this, by the way. Okay. Open circle all the way up. Okay, so let's see what's happening here. Which means on a graph, if I'm sketching it, on x and cost function going up here, that it's going to not be able to, this will be a vertical asymptote, and then everything will be on that side of the x-axis. There'll be nothing over here. Okay, so that's my phone going off. I'll check that in a minute. So let's see, can we simplify this up a little bit? It'll be 2x squared plus 32 x to the negative 1. We're going to find its derivative because we're looking for the critical values. Remember, don't set this equal to 0. You need to set the derivative equal to 0. That's my derivative-friendly form of the derivative. My solving-friendly form. We're going to set that equal to 0 to find the critical values. That's the only part that I care about. Common factor out the 4. 32 divided by 2 is going to be 16. It's going to be 8. And following the argument that we had before, we can say that x equals 2. But if you really want to impress the people around you, you can say omit complex roots. And that lets everybody know that you know what you're talking about, and you don't have to bother going through it, but you know that there's 2 other complex roots here. Okay, so we have one critical value on the domain. That means we have a choice. We can use the intervals chart, or we can use second derivative. Let's see how hard the second derivative would be. Not hard at all. I'm going to take the second derivative. So, the second derivative is going to be 4 plus 64 x to the negative 3. Which is simply 4 plus 64 over x cubed. Well, we know that x must be greater than 0, so there's no way that this will ever be negative. There's no way the 2 together will ever be negative. So you know that this will be, what was our value we came up with, 2? And is concave up everywhere. So if it's going to be concave up everywhere, it looks kind of like this, which means that we have, therefore, C of 2 gives an absolute minimum value to the cost. And you can go back and find out what that is. Looking backwards, I'm finding my cost equation. It is here. It looks like this. No biggie, we can work with that. So that's just going to be 32 over 2. And so it's going to be 8 plus 16, which is 24. If you want to have some fun, go to Desmos graph. Desmos, I don't know. Is there neat? No, it can't be neat. Anyway, it's on your front page of your landing page for the LMS. And go and have it sketch your original function, this guy. take a look at it. And that way you'll see how what we're doing is actually just an application of curve sketching. Okay, ladies and gentlemen, that's it. We'll see you tomorrow. Take care.